I introduce you now to the beast from Cologne, Ismail Khoffi.
Hey, good morning, GM. Thanks for the introduction. I'm going to talk about Celestia, the first modular blockchain, and how it brings scalable shared security to the Cosmos, to Cosmos chains and beyond that. So let's jump right into it. So first about me, I'm Ismail Khoffi. I'm the CTO and co-founder of Celestia. I previously worked as a Tendermint core engineer. And before that, I started my journey in blockchain scaling and crypto at at EPFL as a research engineer. Before that, so you can find me on GitHub and on Twitter. So what I'm going to talk about is briefly an overview on Celestia, what it is, how it works roughly, and then what benefits it brings. And also, Celestia introduces a new paradigm. It's like the first modular blockchain. And so I'm going to talk about like the benefits of Celestia and modularity in general, or like modular blockchains in general. So what's the motivation? Like why Celestia? And I'm gonna start with something that most of you, like at least the developers in the audience, are familiar with. So if you think about like why Cosmos is like why it's easy to like deploy your own like application or your own app chain in like the Cosmos, is mainly because one of the main reasons, I think at least, is because of the separation of concerns in the software, right? Like you have Tendermint, the consensus engine, and you have on top of that communicating via ABCI the state machine and the execution engine. Usually a Cosmos SDK app, but it could be anything, right? Like there's also applications that run on Haskell, or I don't know. You have like a rich set of like execution environments, and that's only because of that like simple abstraction and separation of concerns in software on one chain. So Celestia basically takes this idea and takes it way further in the sense that instead of doing this on one chain, it applies that same paradigm onto like separating it further, that the state machine, like the execution, basically runs on a separate chain. So what's the problem with like current shared execution environments, so like current blockchains? If you think about it, like how does a blockchain work? How do you validate how do you verify if a block is valid? There's basically two things. You check if a block has consensus, and then you verify if all the transactions are valid. So why is this problematic? If you think of like, for instance, Juno, as was presented before, if Juno becomes very, very successful and you have like these many applications on there, you will eventually hit the problem that you cannot execute or like verify efficiently the like all the transactions because there are just too many, right? Like it's like a main bottleneck on shared execution environments. You can see this in Ethereum. It becomes slowly more and more expensive, or you keep the blocks really small, right? And Celestia changes this paradigm, and instead of asking like, does the block has consensus and are all the transactions valid, it instead guarantees two things. Like if you want to verify if a block is valid, instead you go and ask, does the block has consensus like before, like the header, does it have consensus? But then instead of asking like, is every transaction valid, you only check if it's available. So that's the main difference. If you think about it, that's all you need to build an application on top of a blockchain. Because if you have the transactions available, you can go and download them and reapply the state, right? So, but this means that the base layer here, like this new design, doesn't have knowledge about what the application transactions actually are. It sounds counterintuitive, but this is like the main idea, and I explain why this is very beneficial. I mean, it removes the main bottleneck, right? Like it removes the execution bottleneck on the base layer. So how does this work in more detail? So it's like I want to cover like how do we guarantee, what does it actually mean for transactions to be available? How do you guarantee that the transactions are available or the data is available? How do you make sure in a shared execution environment, how do you make sure, in a shared security environment, how do you make sure that you only need to care about the transactions of your application? Because I said like in like this previous paradigm with like shared execution environments, you have the problem that you basically need to download and execute all the transactions. Here, we only want to download the application-specific transactions that you care about. How do you do this? And then also, I said like, okay, we just remove execution. So where does execution actually happen? So to the first point, like how do you ensure that the data in a block is actually available? Is sure, you're like in traditional blockchains, you just download the whole block, right? And here we apply a technique which is called erasure coding. So you think of like the block data, and you arrange it in a square, and then you apply erasure coding, which is like a very simple technique used in CD-ROMs, for instance, right? Like if you scratch a CD, you can still listen to it to some extent because you can recover the data. And so we apply the same technique and add parity bytes. And by this, you get the property that if you sample like random samples from the block data, you get probabilistic guarantees that all the data is available. And this means you can only download like a percentage of the whole block and you have almost like 100% guarantee that all the data is available. So that's how this validity check on availability is done. To the second point is like, how do we make sure that you can, as an application, only download the transactions that are relevant to your application? Is instead of using a binary Merkle tree, we use something called a namespace Merkle tree. It's like it's also a binary Merkle tree, but you each node there basically has a range of namespaces, like basically application domains, so to say, and they are ordered. And every descendant of that node only includes that namespaces. So then you can go as an application and only get your application-specific data. And execution, where does actually execution happen? So when my co-founder Mustafa Al-Bassam came up with the idea, back then he wrote a paper called Lazy Ledger, and there he had this idea of client-side smart contracts, right? Like client-side execution, where you post the data on chain and then you execute them somewhere else, basically, like on the client. The problem with that was that you do not really have like light clients. But shortly after, this concept of optimistic rollups gained more and more traction, and there the execution happens on a separate chain. So basically, it's still client-side execution, it's still the same concept, but basically what you do is you have a chain that doesn't do its own consensus, submits the data onto this data availability layer, onto Celestia, for instance, and you guarantee the validity to light clients, you guarantee the validity to these block headers and the data by either having validity proofs, like ZK rollups, or you have state fraud proofs. This is the other paradigm where you like have to wait a certain period of time, and if no one challenged that block, it means that it is valid. So this is like the two paradigms. And basically a rollup is just another blockchain that doesn't, just to reiterate, another blockchain that posts its data on a data availability layer and doesn't does all the execution, and the data availability layer doesn't need to do that. So just to summarize, like previous blockchains are what's called monolithic blockchains. They do all these tasks on one layer, like on one chain, right? Like you have consensus and execution, and on top of that you could have an execution environment, like for instance Juno or Ethereum has, right? And we introduced this concept of like modular blockchains, where this is more decoupled. You have like the base layer only does one thing, and is consensus and data availability, and the execution happens completely somewhere else, like in a different layer on a separate chain. And on top of that, you can have like many different, so this also allows you to have like many different execution environments. So for the developers in the audience, I want to like briefly give an overview on our software stack. Like how do we go about the implementation briefly? So at the core, at the bottom, we have this namespace Merkle tree that I mentioned. We have an implementation for that, and then there's a Reed-Solomon Merkle tree library that does use this Merkle tree and this erasure coding to commit to the data as mentioned before. So we plugged this into Tendermint. So we had to fork Tendermint because like it's not easy to swap this out. And we call this Celestia Core, but Celestia Core is essentially Tendermint. So the validators in our chain, they commit, as I said, to the erasure coded data. So on top of that, we have, as most like Cosmos chains, we have like a Cosmos SDK app called Celestia app. And why do we need this? I previously said we do not do any execution on chain, but if you want to use proof of stake, you have to have some execution at least, right? So this Cosmos SDK app is very minimal state execution, but only specific to like the base layer, which is like proof of stake, transfers, and fee payments. So basically, you could think of it as the base app in the Cosmos SDK, but augmented with one additional transaction type, which is called pay for data, which is like a data carrying transaction. So you you basically point to a blob of data and you pay for the inclusion of that blob on the main chain. So loosely coupled to that, around that roughly, is what we call Celestia Node. And Celestia Node is the layer that does provide you with like replying and requesting these like data availability sampling requests, which is like these random chunks that you download to ensure yourself that the data is fully available. It's interesting because like here we use a different peer-to-peer stack, which is like based on libp2p, and we also make heavily use of Bitswap currently. Okay, so this is like basically on the left, what you see is the base layer. And to be able to develop applications, you still need like dev tooling around this. So we hope that a lot of this dev tooling will be developed outside of like in the ecosystem, but we also provide some of the dev tooling, and I want to briefly touch on some of the things that we're doing. So we have one software artifact called Optimint, which is essentially a drop-in replacement for Tendermint. So Optimint can be used as Tendermint from the point of view of application developers. You just need to replace the imports, and then you can put on top of that, you can put any Cosmos SDK application. So this gives you like the possibility to build something like Ethermint or Juno, or just any Cosmos SDK application that does only one thing on top of Optimint, right? So if you wanted to build a rollup, you could potentially use Optimint. Optimint, as I said, it doesn't do consensus; it just posts the data onto Celestia. And additionally to that, a completely like different stack, or a different targeting different developers as well, is the quantum gravity bridge. It's not really comparable to like the gravity bridge that some of you might have heard of. It's a one-way bridge that just posts headers and attestation of data availability to Ethereum. And why is this useful? In Ethereum, there's this concept called validiums, where you have like an execution environment outside, and then you have like use Ethereum as a settlement layer, and then you still need, even if it's like a zk rollup, you still need to have the data available somewhere, right? And a lot of like Ethereum rollups or Ethereum, they call them validiums. They use what's called a data availability committee, which is like a closed set of nodes that serve the data essentially. So in using the quantum gravity bridge, we and related to like validiums, we introduced the name Celestiums that Ethereum developers can use to instead of a data availability committee, use the proof-of-stake validator set of Celestia to develop their applications. So these are only like 2 options that you can use to develop an application, and we hope there will be like a great variety of execution environments developed further. For instance, like one of my co-founders also has another project called Fuel, which is a very innovative execution environment. Oh yeah, and also worth mentioning to, if it's an optimistic rollup that you're developing, you have to have fraud proofs to have like trust minimized bridges between those. So for that, we are also looking into developing fraud proofs, general purpose state fraud proofs inside the Cosmos SDK. So if any of this sounds interesting to you, come work with us. We're hiring, so we're like currently a team of 20 people. If any of these areas like DevOps, if you're a Cosmos SDK or Tendermint, or familiar with Tendermint, a Cosmos SDK dev, or an EVM expert, or you're familiar with like database optimizations, peer-to-peer networking, or protocol design, if this like fraud-proof stuff sounds interesting to you, I want to talk to you. Please find me after this presentation. So, and then to this maybe quite technical part, I just want to briefly touch on like what are the benefits of this design? What are the benefits of this modular software, like a modular blockchain paradigm that we introduced? So let's recap what is actually a modular blockchain again. So we define a modular blockchain as a blockchain that fully outsources at least one of the components that like a current monolithic chain does, like execution, settlement, consensus, or data availability. So if you at least outsource it completely and don't do that still on chain, that's what we define as a modular blockchain. So this doesn't mean, for instance, like I mentioned in the beginning, if you do that in software, like in Tendermint with like ABCI, this is not what we mean with like a modular blockchain. So what is like the benefits that it gives you? I think one of the key benefits that you gain from that is scalability. If you think of like decoupling these layers and separation of concerns, this means, for instance, that like the data availability layer can focus on one thing and does that one thing very well, and you can optimize for that one task only. And similarly, with execution environments, you can like completely focus on your like execution environment to be fast and efficient. So it's safe to say like the more you specialize, the more you can focus and like optimize there. So like in the case of Celestia, we'll try to optimize for like data throughput essentially, and that's the only thing we'll optimize ever for. Another point is that I didn't really touch on that, but like with data availability sampling, you also gain and fraud and validity proofs. You also have like trust minimized light clients. So light clients get almost the same guarantees as full nodes and traditional chains. And also with like data availability sampling, like light clients have the possibility to contribute to the network, to the security and throughput of the network. So this also contributes to scalability in that sense. Another thing that I already mentioned briefly is like flexibility as a developer. So I'd assume that developers will experiment more and more with like execution environments and innovate there. And also like Cosmos SDK devs might also use like existing execution environments and port them onto Celestia. So like a few of those like the EVM or Optimism or Fuel that I already mentioned, Cosm that was mentioned before, Cosmos SDK obviously. So there will be like a greater variety of like execution environments and also maybe new ones that we didn't think about yet. Yeah, and another point is sovereignty that you only gain with this separation of concerns. If you think about what makes a blockchain valuable, it's actually a social consensus. It's also something that was previously mentioned. So what like makes the hub, for instance, valuable is that people say it's valuable, and there's social consensus. The hub is important, and by separating these concerns further, for instance, by separating computation out of the data consensus layer, you gain the possibility to sovereignly fork out your state machine, for instance. Like you can innovate much faster. You can, like, if you want to fork on Ethereum, you basically borrow into the social consensus of the Ethereum base layer, and you cannot just like on your chain or in your application do whatever you want. Like by separating this, you can like fork out your chain as you please, and I think that's something that we will see a lot. Basically by like having more and more forks, and it's actually a good thing if you think about it. So one last slide, and I wanted to touch on is like what does this all mean for the Cosmos? Like, why is this relevant for the Cosmos ecosystem? So I think, so I think the main point is having a scalable shared security layer. I mean, there's also interchain staking, and I think is like an important step for like the hub. But if you think about this here, you can have a layer that like gives you shared security, but completely permissionless. You can like just deploy your application and immediately start using it and have like gaining traction and having users. You do not need to like convince anyone, participate in like the hub's governance to like be part of that the validators validate your chain as well. You can just like immediately start. And also because of the simplicity because of the decoupling of like the execution and the data availability layer, the base layer doesn't need to understand what you're doing. While in interchain staking, you basically validate, or a subset of the validators validate the other chain as well. So I think this will lead to the fact that you will capture much more applications. Users that usually, or developers that usually would go to a shared execution environment like Ethereum or maybe Juno would also just deploy their own sovereign chains. And I think you will capture, with this, you will gain much more adoption as well, right? Like you can have all these application-specific chains that do not run their own proof-of-stake network and consensus. Yeah, that's basically it. Thank you. So, questions?
Yes, we have a bunch of questions, and sorry about this. Somebody forgot to turn off my mic. Anyway,
no.
So yeah, there are a lot of questions. So I will pick 3 of them, and I'm sure you will be on ground for the rest of the day.
I'm here all day. Yeah.
So the first question is: what is your opinion? Are there main downsides of the modular paradigm compared to the monolithic one for blockchains?
I mean, of course, there are trade-offs. I wouldn't say it's like there's only benefits, but I think the benefits overweight the trade-offs are worth it. So I think composability for like, if you have like a monolithic chain and a shared execution environment, composability is very easy, right? Like if you think about on Ethereum, all these Ethereum apps, they can like natively bridge on Ethereum. So bridging becomes more tricky. That's, I think, slightly more nuanced and complex. But I think it's worth it because you have like all these sovereignty. No.
I see. And another question is, what are the main differences and trade-offs between Celestia and Polygon Avail?
Okay, so Polygon Avail is very, very similar to Celestia, that's true. The main difference here is that Polygon Avail, as far as I understand, so I talked about like this erasure coding and how we commit to the data is like a plain old Merkle tree. Polygon Avail uses vector commitments instead. So instead of like a Merkle tree, it uses vector commitments. So this is like a bit more expensive to generate these proofs because like it's polynomial commitments. I think that's the main difference, but it also has some benefits. I think from my standpoint, I think using a Merkle tree is way more practical right now, and it's much easier to run like a validator for Celestia than it is to run a prover for like vector commitments. I think that's the main difference. I think we're a bit ahead of like development, but that's, yeah, that can change.
Yeah, and the last question is, in sharing the data availability layer, does a bug or issue there potentially take down all the chains built on top? Is there a risky dependency?
I mean, the coupling is very loose in the sense that, I mean, yeah, if the chain halts and you're building natively on top of Celestia, then potentially your chain would also halt. But you could also, in your rollup, optimistically continue and then post all that data retroactively. As long as it is, I think as long as it is in like a reasonable time frame of like days or weeks, it wouldn't matter too much. Like, it wouldn't take down all the applications on top, potentially. Or if you use like this Ethereum like quantum gravity bridge approach where you run like Celestiums, you could like continue using Ethereum for settlement and wait for the chain to go back live and then post the data there. So no, it's not. It is not an issue, but it's not a big deal, I'd say.
You heard it here first. A big round of applause for Ismail Khoffi, please.
Thank you. Thanks.